Thank you all for coming for today's talk. I will be talking about strength of materials under high dynamic pressures, so which we typically see in high velocity impact applications. So I will start off with a brief background and motivation, why we are doing this work. Then I will discuss about pressure shear plate impact experiment and our research in extending its capability to high pressures to study material behavior at high pressures. Then I'll present results from copper, which is a very good model material to validate our experiment setup. And also we will look at some interesting physics of this material at high pressures, followed by summary. Every year, there are about 13,000 bird strikes happen in the United States. The velocities of this impact can range from 0.1 to 0.2 kilometer per second. Therefore, sometimes this impact can be dangerous. For example, the US Airways flight had to land on Hudson River due to bird impact in 2009. Miraculously, everyone survived the crash landing. So in the impact loading, a high amplitude load is applied for a very short period of time. Therefore, the strain rates and pressures involved in these applications are quite high. And if you look at even higher velocity impact applications, such as ballistic impact and high space applications, the velocities can range from 0.5 to 25 kilometers per second. So if you take hypersonic vehicles, it has to travel through dust and different weathers. So therefore, the velocity by which these particles are hitting onto these structures are extremely high, which actually generate extreme pressures and strain rates. So therefore, we need to understand material behavior at such loading conditions to design future materials and understand such phenomena to develop very reliable constitutive models. So if you look at the strain rates and pressures involved in these kind of applications, we can actually plot an X and Y plots. Here, X is in strain rate and Y is the pressure. And if you look at the automobile accidents, they're happening at strain rates close to 10 to the power 3 per second, whereas the pressure is relatively low. And if you go to hypersonic applications, the pressures can be quite high. It can go as high as 100 gigapascal, and the strain rate can be over 10 to the power 5 per second. So in these kind of pressures and strain rates, the material behavior is dominated by the formation of shock waves. The failure under these loading conditions are mainly due to spallation and fragmentation, which has direct relation to the strength of the material. Therefore, we need to understand how strength of material changes at these kind of pressures and strain rates. So what are the different experimental tools we have to study material behavior at these pressures? So one of the main and very well used experimental technique is plate impact experiment. As the name says, an impactor, a thin plate impacts a target at high velocity. So this is a thin circular impactor, and which impacts a target at high velocity, which generates shock wave both in target and the impactor. So this is a shock wave that's traveling in X direction. At the same time, the edge of the freeze of a boundary wave from the edge travels towards the center of the sample. So if you take the material point at the center, it is under uniaxial strain condition due to inertia confinement before the boundary wave reaches the center. So if you take the strain tensor, it will only have the first component as you see here. And the stress tensor, you have the stress in the diagonal component. You have only the diagonal component in the stress tensor, with sigma x is the stress in X direction, and sigma y and sigma z, which are equal in an isotropic material, and that is actually that is nothing but the inertial stress in the material. So what we typically measure in this experiment is the free surface velocity and the shock wave velocity in the target. So to measure the shock wave velocity, we can actually find the transit time of the shock wave in the target. And the free surface velocity is typically measured using velocity interferometry using photon Doppler velocimeter. So this is a typical particle velocity profile for an elastic plastic material. So initially it has a very short rise time, and it reaches finally the Hugonian elastic limit, which is nothing but the elastic limit of the material under uniaxial strain conditions. After that, it has a specific structure, and this is called structure of the shock wave, which is function of both strain rate and pressures. And then it reaches the final Hugonian state. And if you design experiment for spar failure, one can also study the tensile failure using these experiments. So if you look at this shock wave velocity versus particle velocity relationship, for most of the material, it has a linear USUP relationship. It's also so-called equation of state of the material. So if you know the equation of state of the material, we can calculate the stress in the sample, the stress in the longitudinal direction, which is actually the sigma x, that is the first component, the stress tensor. However, to get the shear strength of the sample, we need to have an information on sigma y or sigma z, which we don't have from a normal experiment. So as I briefly mentioned, the structure of the shock wave is function of both strain rate and pressure. And it is very clear in the from the experiments in the past that how strain rate affects the strength of material. So if you plot flow strength versus strain rate, after a critical strain rate, the strength increases drastically, as you see here. However, it is not very clear how the pressure affects the strength of the material. And every impact problem is a coupled phenomena where you have both strain rate, pressures, and temperature. So we need to understand what is the relative contribution of pressure, strain rate, and temperature on strength of materials. However, the experimental tools that can actually control pressures and strain rates are extremely limited. Therefore, in today's talk, I will talk about pressure shear plate impact experiment. It's a powerful technique that is developed in Clifton's lab in 1970s, which allow us to investigate material at different strain rates and pressures. We can also control the strain rate and pressures independently. So this is a slightly different from normal impact. Here, an inclined plate impacts a sandwich assembly where the sample is sandwiched between a front and rear anvil, as you see here. So when you impact it at high velocity onto this front anvil, if you look at the XT diagram of this experiment, so there will be since it is an inclined impact, it generates both longitudinal and shear wave in the front anvil. Since the longitudinal wave is always faster, it reaches the sample first and reverberates within the sample and reaches to the pressures this experiment is designed for. Then the shear wave comes and shear the sample, and this information can be used to calculate the strength of the material at high pressures. So in this experiment, what quantities we typically measure is the projectile velocity and the free surface particle velocity, both normal and transverse components. So in order to do that, we have deposited a diffraction grating using E-beam lithography on the backside of the rear anvil, as you see here. So if you shine light onto it, it diffracts zeroth and first order diffraction, higher order diffraction patterns are also present. However, we use these three diffraction patterns in measuring the free surface particle velocity. The zeroth order is used for measuring the normal particle velocity, whereas the first order is used for measuring the transverse particle velocity using heterodyne transverse velocimeter. So the time resolution for this experiment is 1/1000th of a second with a velocity resolution close to 0.5 meter per second. So how can we get the strength of material with this experimental technique? So conventionally, if your anvil stays elastic, one can calculate the normal stress in the sample by using method of characteristics. So the normal stress in the sample can be calculated by knowing the density of these anvil plates. C1 is the longitudinal wave velocity. UFS is the free surface particle velocity, normal particle velocity, which we measure using PDV. Whereas the shear stress can also be calculated by knowing the density. C2 is the shear wave velocity. VFS is the transverse particle velocity, which we measure using our heterodyne transverse velocimeter. The shearing rate also can be directly calculated from the initial impact velocity and the free surface particle velocity, which we measure, and H is the thickness of the sample. So we can independently control normal stress and shearing rate by changing the angle by which the flyer plate impacts the front anvil. However, the main challenge here, most of the anvil material are currently available has a Hugoni elastic limit close to 10 gigapascal or lower. So diamond obviously have high Hugoni elastic limit, which is close to 35 GPa, but we cannot use diamond for these kind of experiments. So we need to have a different technique or to actually extract the strength of material at high pressures. So we developed a hybrid method to actually expand this experimental capability to high pressures up to 50 gigapascal. So first we do experiments on anvil material. It's a two-step procedure. First, actually, we do experiments on anvil materials at high velocities and calibrate a material model for the anvil material. So once you have the material model for the anvil material, the only unknown we have in the sandwich experiment is the copper sample. So we use all these plates to be same. Therefore, we know the material model for these plates. The only unknown is the sample that is sandwiched between these two plates. So then we do sandwich experiments and use numerical simulations to infer the strength of the sample that is sandwiched between two anvil material. So again, it's a two-step procedure. First, we calibrate the anvil material, then we do the sandwich experiments, and which is used to get the strength of the material at different pressures. So how we do this experiment, we use a powder gun, which can go up to 1.5 kilometers per second. And we burn rifle powder on the backside, as you see here, which actually drives the flyer at high velocity and which hits the target. And that actually triggers the oscilloscope, which collects the information on the velocity. So the powder gun with a bore diameter is has a bore diameter about 140 millimeter, and we have a slot in the barrel, so which actually allow us to so in order for not to rotate the flyer in the gun. So first we do a symmetric experiment. So we actually use tungsten carbide as the anvil material, and we have done an experiment at 3 impact velocities ranging from 390 to 928 meters per second, which sets a pressure of close to 14 to 42.5 GPa. So the skew angle we change from 18 to 3 degree, and the tilt for all the experiments is below 1 milliradian. Tilt is the misalignment between the flyer and the target plate during impact. So this is the normal particle velocity we measured for 42.5 GPa, and this is for 26.5 GPa, and these are the transverse particle velocity we measured for these 3 different impact experiments. So we calculate the Hugoni elastic limit of this material to be close to 6.5 gigapascal. And as you see here, at 42.5 GPa, we have significant plasticity in the anvil material. So the pressure at which these experiments are done are about 6 times the stress the Hugoni elastic limit of this material. So now we have to calibrate a material model for this for the anvil material. For that, we actually use a strength model, as you see here. The strain, it has a strain rate, strain hardening, power law strain hardening, a copper cement strain rate hardening, and Johnson-Cook thermal softening. The volumetric behavior is modeled by using a well-known linear USU relationship for the tungsten carbide. So as you see here, with these parameters, these final parameters, we have a very good match for both normal and transverse particle velocity profiles. So one point I want to emphasize here. So in this experiment, since we have both normal and transverse particle velocity, so we need to match both normal and transverse particle velocity to have a unique parameter for these material models. So as you see here, we have a very good match for both normal and transverse particle velocity for all the experiments we have conducted. As you see here, this is the experimental profile. The solid line is the experimental profile. This dotted line is the simulation that actually shows very good match with our both normal and transverse particle velocity profile for all the experiments. So what we have done here, first we actually calibrate a material model for these 2 experiments and see if we can recover the observed behavior at 42.5 gigapascal. So now we have a very good material model for the anvil material, and now we can do the sandwich experiments for studying the strength of the copper. So sandwich experiment, as I briefly mentioned, so where we actually impact a flyer plate at high velocity onto the specific configuration, as you see here, where the copper sample is sandwiched between 2 anvil plates. So we have done at 3 different impact velocities ranging from 210 to 925 meters per second. The skew angle is changed from 12.5 to 3 degrees. So why we change the skew angle is to have a same strain rate in the sample that is sandwiched between these 2 anvil plates. So this experiment will give us at a fixed strain rate what is the contribution of pressure on strength of the material. So as we all know, the copper is an FCC material and the microstructure is shown here. The sample thickness is about 170 micrometer and which has a parallelism within 2 micrometer. The diameter of the sample is close to 30 millimeter in this experiment. So now we look at how actually our normal and transverse particle velocity looks like in copper at different pressures. So if you look at the normal particle velocity profile, it's not very different from our symmetric experiment, and we don't expect it to change because the sample that is sandwiched between these two anvil plates are very thin. Therefore, the stress wave, the normal stress wave that is coming from the anvil will actually transfer to the rear anvil without much dissipation. However, the transverse velocity profile is very, very different from our symmetric experiment, which actually the direct consequence of the sample, the shear strength of the copper sample that is sandwiched between these two plates. As 10 GPa, the peak transverse particle velocity was observed to be about 8.6 meter per second, which increases to about 13.7 meter per second when we change pressure from 10 to 42.5 GPa. The strength actually changes at this when we change the pressure from 10 to 42.5 GPa. This is actually the direct indication of the strength enhancement we see at different pressures. So now we have to do the simulations to get the strength of the material, and we need a pressure dependent model. As you see here, we have used a very well-known Steinberg-Cochran pressure dependent model, which was calibrated in the past for OFHC Copper. However, so one of the main assumptions in this model, the rate at which your shear modulus changes with pressure is equal to the rate at which your yield strength changes with pressure. So this is it's a very well-known assumption for this material model to calculate this, to actually get the pressure dependent strength of the material. And we also look at if the shear modulus scaling, which was calibrated in the past, is actually reliable. We calculated the shear modulus as function of pressure with Burakovsky-Grief-Preston model, and which actually shows it's very close to what is calibrated in the past. So now we will use this model and see how it actually behave in our experiment. As you see here, this is the experiment, and our simulation actually underpredicts the transverse particle velocity, which is telling you the shear strength, the yield strength of the material is actually scaling differently from your shear modulus scaling, which was assumed previously in many models. So now we change the scaling to about 2.5 times the shear modulus scaling. So that gives us the yield strength scaling parameter to be about 65 terapascal inverse, and we have actually very good match for both normal and transverse particle velocity profile. As you see here, this is the normal particle velocity profile from 10.1 GPa, and we have relatively very good match for the normal and transverse particle velocity profile. So this is a 5% bound, and we have match for both, which we have matched for all the experiments. The transverse velocity profile is matched for all the experiments. So now we can actually look at what is the shear strength of the material at these 3 different pressures. So if you look at the shear stress versus shear strain curve, the strength increases by about 3 times when we change pressure from 10 to 42.5 GPa. As you see here, at 10 GPa, the strength is about 180 megapascal, which increases to about 600 megapascal when we change pressure from 10 to 42.5 GPa. And if you look at the flow strength versus strain rate plot, where we fix the strain rate at 10 to the power 5 per second, which increase and change the pressure from 10 to 42.5 GPa, and that shows the strength increases by about 3 times when we change the pressure. And it is known that if you change the strain rate, it has the strength should increase in this fashion. However, we still don't know if we fix the strain rate and if it's going to follow the same behavior as it is actually showed in the strain rate regime before. So this is actually a subject of future study. So this study actually shows we need to have one more axis with pressure to have a complete description of the flow strength in these kind of high velocity impacts. So to summarize, so we actually extended the capability of pressure shear plate impact experiments to study material behavior at high pressures, and a new method incorporating anvil plasticity is implemented and validated. The PSPA experiments reveal that the flow strength of the copper increases by about 2.8 times when we change pressure from 10 to 42.5 GPa at a fixed strain rate of 10 to the power 5 per second. And also, we have seen that the shear modulus scaling and the yield strength scalings are very, very different for copper, which was assumed to be same in the past in many, many models. With that, I want to actually conclude, and I want to actually thank many collaborators in my work, and especially Kaushik and Jeff Burigdelu, Zeb Lamenture, Suhas Premila, who is actually a speaker in this session, and the funding that is given by different agencies. And thank you for listening to me, and I'm happy to take any questions you might have.